We were sparks on quiet streets, two hearts finding where to meet. But life pulled us apart, left me talking to the dark. If I called you tonight, would it feel the same? Or have we both moved on to different names? Take me back to the start, before the quiet and the scars, when the world felt small and your hands felt warm. Take me back to the start, if only for a moment. I've been up since 3, scrolling back where we used to be, half truths in this late night chat, both of us knowing what a life had.
Hello, welcome to Let's Get to the Marks. I'm doing a 2-hour live only tonight because I've got chemistry A level to do as well. So I'm doing 6 to 8 on a GCSE, and I'm going to do a little bit of chemistry A level as well after that, hopefully. We'll see how things roll. I might die before then. You never know. Right. Yeah, just going through some little bits and pieces. There will be other YouTubers going on live, so I thought, well, I'll coincide mine with an early one, and then there's some other people that start later, so you can watch them as well. That way you get the best of both worlds. It's kind of going to be a bit of both, combined and triple. And so there we go. All right. Let's go through. So what we're going to do is what can I say, peeps? We are going to, yeah, you got your physics tomorrow, so good luck. I hope the biology and chemistry went well. Hope you managed to do some revision over your half term. Well, if you didn't manage to, you still got time tonight to watch some YouTube videos. So there's my one, which is going to be a quick one tonight, and then there's other people's ones which are going to be on after mine as well. So awesome. Yep, get your pen and paper and your calculator. It's physics, peeps.
Here we go. What?
Alright, just a quick warm-up, although it's not really a warm-up. These are difficult questions to start with. So I've got 4 little multiple choice questions that are on topics that could come up in tomorrow's exam. Gosh, imagine it was today. Oh my gosh. So let's have a little look what we got going down. So you might want to have a go at this. Yeah, the live is recorded so you can watch it later. It's only going to be 2 hours. I'm not going to get through everything. Like with my other ones, I've tried to get through the whole course. I'm not going to bother doing that because I've got A level to do as well tonight. It's one of them. I could have, like, some years I've sacked off the A level and been like, pfft, but this year I said to myself, I'm going to do some for the A level as well tonight. So sometimes there's a clash when there's 2 exams going on the same day. So there we go. So, yep. The first question says, which of the following shows the typical output potential difference for a dynamo? And then we have water as a density of 1,000 kilogram per meter cubed. Water of volume 1 meter cubed is frozen. The volume of ice formed is 1.09 meters cubed. What is the density of the ice? You've got to use the equation sheet, but you might know that density equals mass over volume. And then 2 balloons, A and B, repel each other when placed close together. Which row in the table explains why they repel each other? And then the torch contains 1 LED, 1 switch and 3 cells. Which diagram is the correct circuit for the torch? I will go through the answers. You might be sitting there like, what the beep? These aren't the easiest questions, these 4. So I'll get you thinking. Which of the following graphs shows the typical output voltage? Well, dynamo. The trick here is that a dynamo, it's kind of like paper 2 dynamos really, but dynamos are direct current. So they're really asking you which one is DC or DV, direct voltage, direct current or direct voltage. And direct current only goes one way around a circuit, so it's only going to be in one side, either the negative or the positive. And so it can't be this because this is in the positive and the negative, so that is AC. It can't be this because this is in the positive and the negative, so that is also AC. You might say, so it can be D or B, sir, and you kind of be right, except for this is a waveform and this is analog, like a digital signal. So the answer is actually B here. It's only in the positive, so it's a direct current. Now for this one up here, water has a density of 1,000 kilograms. We need to know density is equal to mass over volume. You will get the equation sheet. Bosh, so that means that 1,000 kg per meter squared. That actually tells you the equation. They've divided kilograms by meter cubed. So 1,000 is equal to something over meters over 1.09 meters cubed. So 1,000 is equal to something divided by 1.09. So let's you can just times those two together and you'll get the answer. So if you want the volume, density is mass over volume. No, what do we what? No, they're asked us for the density. I'm talking at my backside. Sorry, talking at my backside, folks. What am I talking about? He's lost the plot. He's lost the plot. Do 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 do. Oh my days, what is going on there? Right, so we've been given the water of volume of 1 meter cubed is frozen. The volume of the ice formed is 1.09 meters. What is the density of the ice? So we've got whoa. So that means the volume is that we have that's 1,000 kilograms per meter cubed. So we've got 1,000 kg is the mass. So we got mass over volume over 1.09 meters cubed. That was a difficult one. Equals the density. Okay, so we know when it was 1 meter cubed of water, we're going to have the same mass. Mass doesn't get lost. If you freeze ice, it's not heavier than the water you froze, so the mass doesn't get lost. It said the volume originally was 1 meter cubed and 1,000 kilogram per meter cubed, so the mass originally was 1,000. So we know we're going to do 1,000. God, this was starting off with some disgusting questions actually. Over 1.09. So this is going to be 917 kg per meters cubed. So there you go. And that's why ice floats, because it has a lower density than water. So if you know that ice floats, you'd know the density will be less than that of water. Anywho, let's look. Two balloons repel each other. They've got to have like charges. Equal numbers of protons and electrons, more protons. No, so this would be positive and this would be zero. So we're not going with that. Equal numbers of protons and electrons equal. No, that would be zero and that would be zero. They're repelling, so they've got to have the same charge. More electrons than protons, more electrons than protons. Yes, it's going to be C because these will both be negative and like charges repel. So, whereas that would be plus and that would be negative, and these bad boys would attract rather than repel. So the answer for this one is C. And then the torch contains one LED, one switch and 3 cells. Which diagram shows the correct circuit for the torch? Well, this cannot work because the battery has been put the wrong way. It's always got to be plus to minus, plus to minus, plus to minus. That's got like minus to minus, so that ain't going to work. Now, diodes will only let current flow in this direction, the direction of the arrow. This is called a diode. It's actually an LED. It's a light emitting diode. It's an LED, but nevertheless, it will only let light flow through in that direction. Now, current goes from plus to minus, so current is flowing that way, so no, that won't work. So the answer is over here. This is the answer, the third box, because current will flow this way around the circuit. It will go through the diode that way. It's the only way it can go through. So there we go. Hope you got them right. Well, it's kind of a mix of both. Yeah, I'm going to go through all that. Anyway, zinging on very, very quickly, just to remind you, there are like 8 different types of energy. So, just remember that there are different types of energy. You've got thermal energy, kinetic energy, gravitational energy, elastic energy, magnetic, nuclear, chemical, electrostatic. The most common they're going to ask you about is thermal, kinetic, and say gravitational and elastic. Those top 4 are probably the most common. They might bust out chemical. They rarely talk about magnetic, nuclear, and electrostatic. but these are stores of energy. So my body has all of these stores, 8 stores in it. There are 8 energy stores, and we can increase the energy in those stores. They can be transferred between those stores. So you can transfer energy from the chemicals, the food you ate, into heat. Right now, giving off heat and kinetic. I'm waving my arms around. So I'm transferring chemical into thermal and kinetic. Now, how do we transfer between the different energy stores? There are 4 methods for transferring. One is mechanical, so moving stuff, like moving my arms around, transfers the chemical into thermal and kinetic. So there's mechanical, but there's also some other ways to transfer energy. So these are the energy transfer methods. Mechanical is when you're doing work and you're moving something, like if I lift my calculator, I am transferring chemical energy from my body into gravitational potential energy. I'm transferring chemical energy into the gravitational potential store, I should say, but I'm using mechanical as a transfer. This is not an energy store. Mechanical. Electrical is not an energy store. It's a way of transferring chemical energy from the power station to your home. And then thermal is a way of transferring energy. You can feel heat coming out your coffee cup. And light, of course, transfers energy from the sun. And sound. These are all methods of radiation: thermal, light, and sound. Right. They're all transfers. What else? What else? What else? You're going to come across situations where they talk about a system. A closed system is a group of objects where you can't add energy or take away. You can just transfer between the objects. So watch out for that. They'll talk about closed systems. Work done. They'll talk about work being done. Work done is a way of just saying energy transferred. So work done is energy. So if they ask you the work done by a car, for example, it's just saying how much energy does it take to stop the car moving. So work done is just another form of energy. Just watch out for that. Now, I want to go through some bits and pieces. We're going to do a load of questions. So, yeah. Specific heat capacity practical. I hope everyone's good with this. Just familiarize yourself. You wouldn't have a big fat hole like that. That's a well dodgy hole. But the specific heat capacity practical involves an aluminium block or an iron block or a solid metal, and then you connect it to a joule meter. You use a thermometer to measure the temperature before and after, and then you need a power supply that's going to supply energy into the block. The joule meter will measure how much energy has been used, and you will do the temperature change, and you can work out from this the specific heat capacity. And you'll need to talk about, you guys are going to want to know, you're trying to work out the change, that triangle means change, the change in energy, and the equation on your equation sheet is going to be mass times specific heat capacity times the change in temperature. I like to use a T, but on your data book in AQA, they're going to use this. So you need to talk about how you would rearrange this to find C. So we would do delta E, and we would divide that by M times the change in temperature, and that would get you marks in the practical to say, look, this is how I'll find the specific heat capacity of this aluminium block. And then you would literally go through the equipment. What could you use to find the mass of a block? Now, they have done it before with a beaker of oil, and you've had to say pour the oil in a beaker, put it on a scale, weigh the beaker without the oil, and then with the oil take away the glass beaker, and then you know the mass of the oil. So you can weigh an aluminium block really easy on a scale. That will give you the mass. The change in temperature, you just turn the power supply on. You take the temperature at the start, then after 5 minutes or after 1 minute, however long a length of time, you take the temperature at the end, and that is your change in temperature. Now, the energy added can be measured. This measures the joule meter. You must remember that. That measures the energy transferred. Now, you can use an ammeter, and you can use a stopwatch, and you can use a voltmeter to work out the energy added, because power is equal to, you can work out energy is power times time, and power is I times V. So you can do current times voltage times time, and that will give you the energy added. But that's long. So if you want to, you can add a voltmeter and an ammeter in there and a stopwatch, and then you can do current times voltage times time and work out the energy that way. But just remember a joule meter and you're snorted. Right, let me give you a question on this. Um, let me give you a question on this. So let me give you a specific heat capacity question. We're going to do a couple of questions on specific heat capacity. So we'll do a practical one, but we'll also do one how to use the equation. So bear with me while I just whip out a specific heat capacity equation for you. Do we want a difficult one or an easy one? Let's go with... Okay, this is a bit of a weird one. This is just applying the equation. So let me just show you one where we're going to apply the equation. And we'll have a go at this one. What? Oh my gosh. I've lost the plot. Where's me, why is that on fade? What the... No. What the... Let's go... Oh my gosh. That's some dodgy thing there. Alright, let me just... Hello, you can just see me eyeballs. There we go, folks. See if you can select the right equation and see if you can calculate this. Let me just move that down. Where's my camera? Kamarowski. I probably could have done that without doing that, but never mind. Alright, let's have a go at this one. I can do it all, but it's all about the time. So this one is not the practical version. This is just the equation version. So you're going to be in a panic. You're going to be, oh my God. Right, they've asked you calculate the temperature change. Now the symbol for temperature change is going to be this in AQA, which is a little bit, I don't like that. But you should notice specific heat capacity. So now you scan through your equation sheet and you go, oh my days. Oh, here it is. Change in thermal energy equals mass, specific heat capacity, and temperature change. Excellente. So we want to rearrange that. You can see that there, although my face is bang over that. So that was dumb. Well, this is the equation which my face is over the top of. Always nice. So now try and rearrange that and get the answer, folks. So mass in kilograms, that's all good. Joules, what is joules? Well, that is E. That is mass of the air, and that is specific heat capacity, and they want us to find the temperature change. So what we're going to do here is go delta E. You're going to divide by mass and by specific heat capacity to bring those over here and leave you with the change in temperature. So let's calculate the change in temperature of the air. We're going to go 0.0. You can bust out your calculator, 30 joules. Put up in the chat if you've worked it out. Bosh. 0.0130 joules, and you're going to divide that by 2.60 times 10 to the minus 8 kg. But of course, we need to times that by C, and C is 1.01. I mean, bit dumb that, isn't it? But there we go. Ooh. Notice, tricky little buggers. Look what they've done there. Anyone see what they've done here? And what they've done here? This is why this one is a hard one. What have they done here? It's a bit of a fat purple line, isn't it? What have they done there and there? Do you notice kilojoules and joules? These are units that are not compatible. So we need to change one of those. We can either change these to kilojoules, and we can do that by dividing by 1,000, or we can times that by 1,000 to change that into joules. So we can do one or the other. It's up to you. You can do 1.01 times 1,000, or you can divide that by 1,000. So it's up to you. So notice this is kilojoules per kilogram and this is joules. We're not allowed to divide joules by kilojoules. So we're going to have to do this. Ba-da-bum, ba-da-bum. I'm going to just times 1.01 by 1,000. That makes it easier for me to put it all into joules. And so it doesn't matter which one you do, you're going to get the same answer. So this will now be 1001 times that. So let's bust that out. So okay, no, it won't be. It'll be 1,010 because I'm a dipstick and I can't. I'm so lazy with my maths. There we go. Lovely jubbly. Oh, come on, T. Ain't got all day for this. Okay, let's do 1,010 times 2.6 times 10 to the minus 8. And that gives us that. And then I want to go 0.0130 divided by answer equals bish bash bosh. 495. So lovely jubbly, we get 495. Well done, well done, well done. Okay, super duper. Now, what I also want to do, bish bash bosh, is give you the practical version of specific heat capacity and see if you can handle the old practicalis. Okay, so let me give you the practical. Have I got one? I hope blooming so. Oh, we've got about enough of them, haven't we? No, I've got millions of these specific heat capacity ones. I'd like to give you a little prac write-up on it so you can test out your prac write-up skills on it. Oh, my good gosh, my good gosh, my goody gosh. No, no. Yeah, so we're going to do it. We'll bus out specific heat capacity. There's loads of other things to bus out. Hold on, Tom. Sort it out, mate. Yes. Yes. Oh, I can't find a question on specific heat capacity. Absolutely typicalis. You know what? I can't find one right now on specific heat capacity. So what I'm going to say is let's get back to where I was, and I'm going to get back to back over here, guys. So I'll give you the quick write-up. If you don't know how to do the specific heat capacity practical, let me give you the quick write-up on how to do this. Really dead easy. Of course, I'm not saying don't add in extras. This is the how to rearrange. So this is how to rearrange equation for specific heat capacity. This is how you're going to rearrange the equation. And the bullet points that you want for your content are basically measure mass. Oh my days. Measure mass. Now, be prepared if they give you a gas or a liquid, you can still measure the mass of those. So measure mass of block on weighing scale or balance, you know, whatever. Whatever. Mass balance. Probably a mass balance would be a better thing to say. Because you want the mass, don't you, really? So measure the block on that, anywho. And if you want, you can add in some fluff, like, ooh, zero it first. If it says give some practical skills to get accurate results, then you want to zero the balance first. And then we want to say connect to a battery or power supply. And then we want to say connect to a joule meter. Joule meter is going to measure the energy transferred. This measures the delta E. So that's going to be lovely. Right. Then attach thermometer. And then you just need to say take initial temp. Take initial temp. Don't use a word like temp. and then take final temp. Now, how long are you going to wait? Well, that's up to you. So take final temp. I'm going to say after 2 minutes. And then you're just going to say, bish, take your data and rearrange the equation. You've got the mass, you've got the change in temperature, time them together, but use the connect to a joule meter. I'd want to say, read the energy transferred, read delta E off joule meter. I need to tell the examiner I recognize the joule meter will give me delta E. So I'm just going to say, look, connect the power supply, measure the mass of the block, connect the power supply, connect the joule meter, attach the thermometer. Hopefully you make a nice tight hole so heat doesn't escape. Take the initial temp, take the final temp after 2 minutes, read off the energy transferred off the joule meter, then slap it all in the equation that we've rearranged like that. 6 banging marks. If you want, you can say repeat 3 times to make it reliable, calculate a mean, blah, 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 blah. Easy peasy. If you're doing liquid with a beaker of if you're doing a beaker of oil and you're doing liquid, then what you do with the beaker of oil is you measure the glass beaker without the oil. Then you add 50 centimeters of oil. Then you measure the mass of the beaker with the oil, and you just add one extra calculation to say take away the mass of the glass beaker from the mass of the beaker in oil, so you know what the exact mass of the oil is. We can't just put the oil straight on the scale because it will run everywhere, won't it? And so we're going to put it in a beaker, but we need to take the mass of the beaker away after. Now we know the mass of the oil, we can place the beaker, we can connect the beaker to wires and a power supply in the joule meter and stick a thermometer directly in the oil, and then we can measure the initial temp and the final temp after 5 minutes, 2 minutes, 3 minutes, whatever you want. All right, let's move on. Yes, you can mention insulation will make your results more accurate and your specific heat capacity will be higher. So the fact that heat energy is lost, it means we get an underestimation of delta T. I say T, I know they've got the theta sign, the circle with the line through it, but basically the change in temperature is lower than it should be because heat always escapes. I mean, that one's really rubbish, but yeah, there's some wool or something around there. So insulating it will give you a more accurate specific heat capacity, but your temperature rise will be greater, or your change in temperature will be greater, and you'll get a more accurate, a more valid specific heat capacity as well. Validity is about your control variables, so controlling the heat loss will make it more valid as well. Right, let's look at real simple pimple. We're going to look at some energy change questions. I'm going to quickly look at some energy change questions. So this is a dude in his little budgie smugglers, and the equation on your equation sheet is going to be GPE equals height times mass times GFS. Calculate the energy in the man's GPE store for 2 marks. So we just need to look at our equation sheet and realize that mass in physics is always in kilograms unless they say otherwise, right? It's not like chemistry where we use grams because we're dealing with small, like, molecules and small amounts of stuff. In physics, everything's in kg. So we literally, to work out the energy in this man's body for 2 marks, we're just going to do 3.5 meters. You should be able to do this. Put it in the chat if you've worked it out already before me. That's not hard. 3.5 times 80 kg, and then times GFS. GFS on Earth is normally 9.8. They should tell you in the question because, yeah, otherwise you could be bussing out 10. So it depends. Sometimes they'll bust out 10. So, oh wow, boom! For Lily Mackey's, it is 2,744. So we've got 2,744 joules. Now that's the GPE in the man's body. Okay, let's move on. Right, this comes to an important concept. Energy is transferred from one store to another, and very typically with GPE we transfer it into kinetic energy. So the GPE lost, as the man falls halfway, his kinetic energy, his GPE will go down from 2,744 to half that amount. But that energy has not gone to the surroundings, it's been transferred into kinetic. So at the halfway point, he'll have like half that amount of GPE and half that amount of kinetic. Anyway, this equation you'll find on your equation sheet, and they often link the two together. So his GPE was 2,744. The man enters the water. His GPE is transferred all into KE. That's a big assumption, but we're going to make that assumption. Calculate the velocity of the man as he hits the water. Who can do that? Worth 3 marks. Boom. Yeah, I will do a little bit of radiation. Hopefully we get there. Someone's bust out 8.28. Well, here's what you got to do. You got to know how to rearrange this equation, right? So I need to find velocity. So I'm going to do, well, KE. Some people will go 2 times, get rid of the half by timesing both sides by 2. You don't have to do that. And then divide by m. You can just do KE over half m. It's up to you. And what we're going to do is that is going to equal v squared. Now I need to get rid of the squared because the question wants velocity, not velocity squared. So we're going to square root both sides of the equal sign, and we're going to get this. So I'm going to go 2 times 2,744, and we're going to divide that by 80 kg. Now that is the same as you guys doing 2,744 over 40. You'll find you'll get the same answer. So you can rearrange it in the same way, but then I need to square root the answer for both of them. Okay, and see what you get. Good. So people have rounded that 8.3. I'm going to believe you. I believe you. 2,744 divided by 40 equals that. Square root answer. Bish bash bosh. What does it give me? 8.2825. Yeah, we'll go with that. 8.28. Nice. Well done, folks. Yeah, so 8.28. That is meters per second. So the answer for this is 8.28 meters per second is the velocity that he hits the water with. So if you know the gravitational energy, you know the kinetic energy of a falling object. Bear that in mind. It'll often be exactly the same, and they're just testing you on the law of energy conservation. Remember, energy cannot be created or destroyed, purely transferred, and they'll test you on that without asking you that sometimes, just by saying, and sometimes it'll be a 1 marker. They'll say like, what was his kinetic energy? And you'll be like trying to do the kinetic energy equation. You'll be like, oh my God, they've not given me his mass or anything. How do I do it? They'll have told you his GPE, and then you just assume it is all transferred. Now, actually, it would have been less because his velocity would have been like 7.9, because some energy is lost, really is transferred. Where to? It's transferred to the surroundings. As heat dissipated, we say. It's very hard to be useful after that. To surrounded, what the hell? To surroundings as heat. Okay, you know what I mean. It warms up the surroundings due to friction of his body with the air. Cool. Right, what we got? Elastic potential energy equals half spring constant times extension squared. This is another one that can come up. This is a harder one. AI predicts that this is coming up tomorrow, but who knows what AI knows, eh? Probably knows nothing. It's just a glorified search engine at the moment. But elastic potential energy equals half spring constant times extension squared. Bear in mind that extension and compression are the same, so I could do like squashing a spring, and then you just do the before and after to find the extension. The girl extends the elastic band from 50 centimeters. Extends the elastic band 50 centimeters. The spring constant is 70 newtons per meter. Who can calculate the elastic potential energy? So you want to do energy. So we know half K times E squared. So what is half K? Well, half K will be 35 Newton meters. That's half K, right? And we want to times that by E squared. Now here's the issue. Do we use centimeters in physics? We use meters. Meters is the main thing. So divide it by 100. That's actually 0.5 meters. So we want to do 35 times 0.5 squared. So we want to go 0.5 times 0.5 to get the square of 0.5, and then that's 0.25, then times 35. We find that she has the elastic potential energy you should get is 8.75 joules. Boom! And this would probably be 3 fat marks, okay? Now, please bear in mind that they may say they may give you something like the before and after. So maybe it was 60 centimeters stretched, and then they say she stretched it to 110 centimeters. Remember, it's the difference, it's the extension, how much it stretched before and after. That is extending, not the length. It's not length, it's extension. And bear in mind that extension is the same as compression. So they could have given you a question where they say the girl squished a spring and it was 20 centimeters and afterwards it was 5, and your extension then would be 15, because you go 20, it's gone down to 5, your extension would be 15. Extension and compression are interchangeable. Right, let's zing. 35 is for 70, but it's half k. The equation is half times k. So 70 was the k. So we went half k 35, 0.5 times 70 times 0.5 squared. So let me go through that again, because I didn't do that very well. So let's just zing those numbers underneath. Come on, Dot, don't fail me now. Right, here we go. Right, what we're going to do, we're going to just zing this. So look, half k, what is that? This is extension. So we're going to go half times 0.5 times 70 times 50 over 100, because we want it in meters. Look, it's got to be in meters. So 50 over 100. And that should be squared. So that's what we'll whack into your calculator. 0.5 times 70 times 50 over 100 squared. Bosh, bish, bash. Guys, if you are doing triple, you need to know about conduction. And it is literally easy peasy. Conduction is how thermal energy is transferred through solid particles, and it's literally transferred through vibration of particles from one particle to the neighboring particle, and it always moves from high temperature to low temperature, so from hot to cold. And then if you are doing triple, bear in mind that you could get a question on convection currents. What is happening here? Well, these red air particles are close to this fiery pot, and they are gaining kinetic energy. They are moving further apart. Therefore, we would say that the air, not the particles don't expand. They don't get bigger. They stay the same size. The gaps between the particles increase. They become less dense. That material becomes less dense, and so it rises. And as it rises, it pushes down the cold, more dense air to the heat source, and that sets up a convection current going like that. The hot air rises, loses the energy, becomes colder, falls back to the heat source, and then expands, less dense, rises. So we need to talk about expansion, less density, rising, more dense material coming back down, and that is convection current. See if you can have a go at that question there. 3 marks. See what you can get there, peeps. Oh, yeah.
If you push the button,
Would you like it?
Like.
Do it. Do it. Do it.
Okay. Anyone come up with 3 bullet points? Anyone hit the 3 bullets? Here's the 3 bullet points. You might be typing them into the chat, so here are the 3 bullets. Basically, air expands, becomes less dense, less dense air rises, more dense air falls, and is pushed closer to the heat source. Anyway, simple question. Right, triple and combined, you need to know this one. So this is for both of you. Lubrication. Lubrication is essentially where we use oil or liquid. You can use solid graphite as used as a lubricant. in chemistry, we know that, right? Because the layers can slide, all that business. So the lubricant fills the gaps, making the surfaces more smooth. What does lubricant reduce? It reduces friction, means less heat is transferred to the surroundings, and your piece of equipment is more efficient. So you do need to know that. You get a higher efficiency when you lubricate stuff. You have got an equation on your equation sheet, which is essentially efficiency is, you can do it in a decimal or you can times it by 100 for a percentage. It's the useful energy out of something over the total energy in. So if I'm putting 100 joules into a machine and 50 is coming out as useful, and I'm losing 50 to heat, to the surroundings, then I can oil that machine and maybe only 30 joules will go to the surroundings as heat and 70 will go into a useful energy in my machine. So I've increased the efficiency. Okay, so you need to be able to explain that. This is combined as well. Yeah, here's a little question on efficiency. Okay, some of the energy from the wind used to rotate a wind turbine is wasted. Yeah, some's going to be lost as heat. Any machine, everything loses energy as heat to the surroundings, every kind of machine. An engineer oils the mechanical parts on a wind turbine. Explain how oiling would affect the efficiency of the wind turbine. So what you want to do is say, what is the oil? What is it? And how does it affect the efficiency? Does it make it increase or decrease? And then explain how. So what is the oil acting as? And then how does it affect the efficiency? Does the efficiency go up or down? And then the third mark is to explain, like, from the equation. So just to show you that equation, the equation looks like this, and it is a decimal, but you can do it as a percentage. Efficiency, oh my gosh, that is hideosa. What the arse? Right. Sorry, excusez-moi. I should say Sugar Ray Leonard. Efficiency equals useful energy in. No. Useful energy out. Oh, you dipstiticus. Useful energy out over total energy in. You get the idea. So think about it in terms of this. We would say the oil is a lubricant. Get a nice mark. Bosh. Less energy wasted. Bosh. And you could explain that. Less heat lost to the surroundings through friction. So through friction, etc. There's like loads of points I can make on that, but I can't be bothered. And then we want to say, so higher amount, oh my gosh, this is disgusting, of useful energy. This is absolutely foul. That writing's horrible. And then we want to say efficiency increased, because they didn't tell us in the question the efficiency is increased, did they? No. Look what they said here. Sometimes they will say, how would it increase the efficiency? They didn't say that. They said, how would it affect the efficiency? When they do that, that's like a bonus generous mark for saying, look, efficiency is increased. They're giving you a bonus. Yep, friction produces heat. That's absolutely right. Absolutement. Yeah, here's the mark scheme answer for that, peeps. What's the time? 6:42. Oh my god, I better move on because I'm only on for a short amount of time today. So here's the mark scheme answer for those of you that want a mark scheme. The efficiency would increase. Look, straight mark for just, if they don't tell you the answer of the description, you're just going to get a straight mark for that. Like, so the efficiency would increase because the percentage proportion amount of energy transferred is increased. So, or more useful energy, because the percentage proportion amount of energy wasted decreased, so less energy wasted. Yeah. Blah, 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 blah. Mention of friction. Diddly-dee, diddly-doo. Right, what do we want to do? Just very quickly, I need to get off this topic. So, just remember, you got to if you're doing triple, you need to know about insulation of the home. I can't remember if it's in combined as well. So you've got cavity wall insulation. That's foam they fill in the walls. Now, that increases the thickness of the walls. If you increase the thickness of a wall, you decrease the thermal conductivity because the heat has to travel further. You can also put an air gap in the wall. Now, conduction only happens through solids, so you prevent conduction. Actually, that's a lie. It can happen through air, but air is a poor conductor. So you need to be able to explain that. You can have a vacuum there, like in the glass here, you can have an air gap, or you could have a vacuum where there's no air, and then you're really reducing convection. And obviously solids prevent convection. So having a combination of solid and air gaps, basically you're interfering with conduction and convection, you're lessening them. Okay. The only issue is radiation through a transparent subject. You're still going to get heat radiating out of your window. You can't cover it all in tin foil. You've got loft insulation. You can cover that in silver foil. Loft insulation blocks the warm air escaping by convection because there are solid fibers, and solid fibers will not convect, and you trap the air so the hot air can't rise and stuff like that. So essentially you can put fibers in there and they will actually prevent conduction and convection. They will help, and you could cover them in silver to reflect the heat and blah 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 with radiation. Then you've got these things called draft excluders. Again, they're preventing convection, heat loss by convection. And don't forget, there is a practical with this. So please, please, please watch out for the practical with this. There's a little practical where it's just really easy, but they're going to give you a health and safety tip. So boiling water can burn you. Remember, boiling water is the hazard. The risk is burns. So boiling water is the hazard. The risk is burns. How can we reduce it? Don't use boiling water, use hot water, but not boiling. So maybe heat to 70 degrees. What you do with this practical, it's the insulation practical. You can wrap it in different thicknesses of the same material. So therefore, I'm investigating how thickness of an insulator affects heat loss. Now, what you can do with that is 5 different thicknesses, same material. Measure the temperature before and after. So you measure the initial temperature and then you wait 5 minutes, or you measure the temperature every minute and you measure the lowest temperature, and then we measure the heat loss for the different thicknesses, and we can plot the layers of insulation against heat loss, against temperature, something like that. Now you could also do 5 different materials, but then you'll need to keep the thickness the same. You should have lids as well. Okay, I will go over the resistance of a wire prac. Bada bada ba, bada bing, bada bong. Very, very quickly, because this is triple, I'm just going to fly through this. Don't forget, if you're doing triple, you need to know that fossil fuels are non-renewable. They produce greenhouse gases like carbon dioxide, and but they're not all bad. So they're non-renewable and they're not sustainable. They won't be around for our grandchildren and our great-grandchildren if we keep using them. So they're non-sustainable, they're non-renewable. You can't make more of them. They will run out, and they produce greenhouse gases, and they produce sulfur dioxide that produces acid rain. Okay, so why is it that 90% of the energy around the earth is produced by fossil fuels if we know they're bad for all these things? Because they're the most reliable source of energy, and you can ramp them up to meet demand. So if all the hospitals, if there's been a big disaster and all the hospitals are putting all their equipment on to save people's lives, the power stations can throw more coal on the fire and you can get more electricity. You cannot go outside and ask the wind to blow more. So these are more reliable. Now we have to look at the, oh, and don't forget nuclear power, but we'll talk about that in a bit. Bish bash bosh. Wind power, wind turbines, visually ugly, noisy, and interfere with the habitats of animals. But like all renewables, they're never going to run out. Okay, so that's the good thing. They won't run out. The only thing is they're not reliable. It's not, and the way I would describe that is just to say then it's not windy. The wind blows with different strengths every day. And then you've got solar power. Once again, you can't say the sun doesn't shine some days because the sun is always shining. But some days there is cloud cover, so it's weather dependent. So it's not particularly reliable. But again, the good things, no greenhouse gases, just like the wind, no carbon dioxide released, no pollutions, and it is renewable. It will never run out. Much better than those is thermal, geothermal, which relies on heat. And what you do need to know, that the heat is produced by radioactive nuclear fission, radioactive decay, like alpha, beta, gamma, in the Earth's core. So radioactive processes are producing the heat that can be used to boil water. Now all we have to do is pour cold water down a tube we drill in the ground, and that will come back up as steam. It can spin a wheel with a magnet in it, and it will make electricity. So it is renewable, no pollution, because it doesn't give off any carbon dioxide or sulfur dioxide. So it's absolutely brilliant. And if we want more, we can just pour more cold water down. So this one is reliable and it can meet demand. So it's perfect. The downside is it's only found in certain locations. Like we don't have that in the UK. Now you've got hydroelectric. A lot of students don't know, but hydroelectric is caused by the gravitational forces of the moon. So hydroelectric, no, I'm talking out my backside. Hydroelectric is not caused by the gravitational forces of the moon, but it does involve gravitational potential energy to kinetic energy as the water falls. So they might test you on that. What else do you need to know? It's reliable. If I want to open my dam and let more water through, I just press a button and more water comes through. So if I need to increase the power to meet the demand of the population, I can do that. Anytime the population needs more energy, they're watching the World Cup final, everyone's TV's on, I can increase the demand. Okay, I can increase the supply, sorry, to meet the demand. So this is very, very good. The downside is it's expensive and it causes flooding and it destroys habitats. Oh my good gosh, it's renewable and no pollution. So there's like, you just got to kind of know this stuff, and you can actually use a pump and pump water up and store it there to when you need it. Right. This one is known as tidal power. This is tidal power, and this one involves the gravitational potential energy of the moon. This involves the gravitational force of the moon pulling the tides. So it's reliable. We know what time of day, every day of the year, that the tides are going to be at their highest or lowest. So we can rely on these. What else? Wave power is just like wind, so not reliable, but renewable and no pollution. And then you've got the last one, folks. I don't want to waffle about renewable energy sources too long, but there is biofuels. Now, biofuels are kind of good because you can use your waste and you can always plant more trees. Farmers use these. They can burn manure, or we can burn plant material like ethanol that's made from fermentation, and we can always plant more trees. These are carbon neutral. When we burn them, they release carbon dioxide, but the trees we planted, or the plants or the crops we planted, took in that carbon dioxide. So it's even overall if you don't think about the transport. Okay. What else? They can cause food shortages and force food prices to go up because farmers spend their time growing these crops instead of selling for food. Let's move on to some electricity. Is everyone all right? Everyone all right? Everyone all right? Everyone all right? Oh my gosh. So what we're looking at, right. All right, let's look at a bit of electricity. Oh my gosh, running out of time. I need to whip through electricity. Don't worry, there's other people coming on live because I'm doing chemistry later, so I've only got another hour and 10 minutes to lick through the course. So A, B, C, D, E, F, G, H, I, J, K, L. Right, hopefully you know what A is, B, C, D, E, and F. While I have a drink, see if you can work out what those are. Yeah, I'm going for electricity right now. So, hopefully you know what this is. A is a cell. B is a battery. C is a switch. D is a closed switch, so still a switch, closed and open. I ain't going to bother writing that. This is a lamp, filament lamp. This one gets hot and melts eventually. This is a fuse. A fuse is a safety device to prevent fires, okay, and protect your equipment. The fuse wire will melt if a high current goes through. This is a light emitting diode. This is a resistor. This is a variable resistor. And then we have a normal diode. doesn't give out light, but only lets current go one way, just like the LED. And then we have a light dependent resistor and a thermistor. Okay, let's move on. So gonna look at some electrics, and then we'll do some questions on electricity. So what we're going to do here, you've got the setup like this. You've got a battery, you've got an ammeter and voltmeter. Don't forget, in electricity, you always put your voltmeter in parallel around a component, and your ammeter will always be in series. It doesn't matter if it's a parallel or series circuit. Putting my voltmeter in parallel does not make you have a parallel circuit. It's still a series circuit. The voltmeter has very high resistance, so no current is flowing through that voltmeter, okay? Whereas an ammeter has incredibly almost zero resistance, because you want the current to flow through and you don't want to interfere with the current because you want to get the full measure of the current. So the ammeter has zero resistance, the voltmeter has very high resistance, so this is still acting as like a series circuit with this just across there. Now, what we find is that as the wire gets longer, and you can attach crocodile clips and just open them up, we find that resistance increases with the length of the wire. When you do this practical for resistance and length of wire, you want to say, I'm going to use 5 different lengths. You must say a minimum of 5. You might want to say 5 centimeter, 10, 15, 20, 25 centimeters. You can make the lengths up unless they say in the method the ones you should use. Then you want to say connect the battery. You can just memorize this diagram. Connect an ammeter, connect a voltmeter. Now, what do you want? Do you need a variable resistor? You don't for this one, because for this one you are just changing the length, then you are writing down the current and the voltage. Now, you will have to know this equation, and in this practical you will have to say use V over I, V equals I times R, and you're going to rearrange that so that you have V over I equals R. So you're going to say for each length of wire, you can just talk about one length. So you say, like, set up the practical as my diagram, start with 5 centimeters, record the voltage, record the current, divide V over I to find R, call the equipment down, repeat 3 times, and take a calculate the mean resistance with that length of wire. And then you'll say repeat for 10, 15, 20, 25, 4 more lengths. And that's all you've got to do. And then plot the graph of resistance against length of wire. And you should see as the wire gets longer, the resistance goes up. Now, there are some hazards with this, that anytime you use electrical equipment, the hazard is heat and the risk is burns. Now, what we have over here, guys, we have a different practical. This practical can come up. This is a different practical. My good gosh. So this is a different practical. So let me talk you through this one. Because I'm speeding through today rather than doing like millions of questions. So I just want to talk you through this practical. This is a practical where they will say they want you to investigate the current and voltage. So watch out for the words current and voltage. If they say this isn't resistance, we're not calculating resistance. Yes, we're getting I and V again, but we're not doing resistance this time. They will say calculate the current and the voltage, or investigate the current and voltage through one of these 3 things: either a resistor or a wire, an ohmic conductor, a lamp, or a diode. And so that is the clue that you're doing this practical. They will say they want you to investigate the current and the voltage through a resistor, a lamp, or a diode. And all you need to do, if it's the lamp, you're going to do a lamp here, okay? If it's the diode, then you're going to put a diode here, okay? So all you're going to do is say set up the voltmeter in parallel around the component. Remember, it's in parallel. With the resistance of a wire, it was around the wire. This time it's around either the lamp, the diode, or the resistor. And the ammeter is always in series. So you're going to get some marks for saying how to set it up. This time we include a variable resistor. Now the variable resistor, a lot of people get confused with this. This is not really for changing the resistance. Yes, it changes resistance, but this is actually changes current. So what we're going to do is we're going to say use the variable resistor to change the current. Start with 1 amp and then measure the voltage through the component. Record. Then you'll say change the variable resistor to 2 amps, 3 amps, 4 amps and 5 amps. So again, you need 5 different measurements. Each time record the voltage. You're then going to say plot that on a graph like this. So of I versus V. Now there's extra points here, and this AI has predicted this is coming up, this practical. You look at all these graphs. These graphs have a positive side and a negative side. That's why they're like a cross. Notice there's a positive side and there is a negative side. Positive on these graphs and negative. Now sometimes they don't show you that, they just show you this. So be prepared. If you see a graph that looks like that, just what I've circled, that's a filament lamp. They just haven't recorded the negative values. But if you're doing the practical, they want you to record the negative, they want you to record the negative values. So how do we get the negative values? Anyone in the chat know how we can get those negative values? I already went through specific heat capacity experiment. Don't say swap the wires, mean bean. You say reverse the connections to the battery or reverse the battery. So if I was writing this practical up, I would draw this and be like, set up circuit. Now, if you don't know how to do that, just ammeter in series, voltmeter in parallel with a variable resistor, bosh, you'll get the marks. If you can remember that, how to do that circuit, excellent. I'm just writing setup circuit because I can't be bothered, but you would need to explain that. That's 2 or 3 marks just for explaining that if they haven't given you it. Okay, set up the circuit, and then I'm going to say use 5 different currents. Now, how do we use 5 different currents? I need to say by using variable resistor. So I'm going to change the variable resistor. I've worded that badly, but you get the idea. By changing the variable resistor to 5 different currents. Each time record the voltage. Each time record voltage. Okay, potential difference is the real name for that. So record the voltage, but I ain't got that kind of space. And then we're just going to say switch battery and repeat to get negative values. So you're going to swap the battery around and repeat to get the negative values, okay? So you want the negative values down here. You have to swap the battery around, so plus and minus are swapped around, and that will give you the negative values. Notice you'll get the exact same pattern here, exact same S-curve, sigmoid curve with the filament lamp, but over here with the diode, we do not get any readings when we swap the battery around, and that is because the diode only lets current go one way around a circuit. If you turn the battery round, the current will go the wrong way. So remember that a diode, like if I put my diode like this, to set this circuit up correctly, my diode would be like this, and that's because current flows. So just remind yourselves, current flows from the positive to the negative, so it can go through the diode, which, oh shit, excuse me, whoopsie, oh man, my thing's having a meltdown, can't handle it, can't handle it. Come on, son. Right, yeah, that's not really coming out, but if you can see that, it's a miracle. So the current can go that way. If I flip the battery around so that it's plus here and minus here, if I flip it around, it's going to look like that. The current's going to go that way, and it can't go through the diode that way, which is why we get no readings when we swap the battery around with the diode. But that's good, that's what you want. And then you'd say plot the graph. You'd need to say plot IV graph, and bish bash bosh. There are other things you can do, like say repeat 3 times for each reading and calculate a mean. I ain't got that kind of room or that kind of time. And compare results, remove anomalies before calculating the mean. You should explain why you're doing a mean. Right, we're going to have a little look. So, resistance in ohms, we got the LDR. What do you need to know about LDRs? Really important. These are in sensing circuits, so security lights, ring cameras, lights that come on. This is the LDR. You do need to know that as it gets darker, the resistance goes up in the LDR. As it gets lighter, the resistance decreases in the LDR. Now, here's a little pattern that you need to remember. When resistance... So here is something to memorize for your exam. When resistance is low, current is high. That's important. You're probably going to be tested on that relationship. When resistance is high, current is low. When resistance is low, current is high. Inverse relationship. However, the little known relationship is with the voltage and the resistance in a circuit like these sensing circuits. So this is uber important for the tip-top marks. So for the tip-top marks, when the resistance is high in the thermistor, its share of the voltage from the power supply will be higher. So that is a tip-top to note, and we will look at a question on that in a second. So in fact, we might go and do that right now. When voltage, no, sugar, bosh. We're going to do a question on this right now. So when resistance is high in resistor, that was a bit crap, wasn't it? I've run out of room. When resistance is high in a resistor, its share of P Diddy increases of the voltage. Okay, so its share of the voltage increases. Let's go and have a look at a question on that. Let's go and have a little look at a question. Hopefully on the other nights when I do B2, P2, I'll be able to go a bit slower and a bit more like technical, but you know, what you're going to do. Bash, bish, bash, boosh. Why is that making noises? Where are we? What did... Oh, here we go. This is the one I want. It's the one I want. All right. Guys, this is physics revision. There's no phototropism or autism's song walkie. We're not doing that. And we're not doing chem. Okay, so this is the question that I was talking about. This is going to test your knowledge of the relationship between current and voltage, etc. So, what we're going? We've got an LDR, light dependent resistor, is used to turn an outside lamp on when it gets dark. So let's have a little look at this question. This is a higher level question. And it is combined and triple, both. So we have AI says you're more than likely to get a thermistor or LDR circuits question in tomorrow's exam. So have a look at this. Look at how they set them up. They are in series, which means next to each other. Yes, it's in parallel to a lamp outside. We don't need to worry about that too much, but there's a lamp over here in parallel. Now, we've got 12 volts going through these. Now, if you know your circuit rules, so your circuit rules of a series circuit, I don't know why my thing keeps, I need to turn down my notifications because my phone is beeping away. Let me turn down notifications. How do I do that? Oh my gosh, nice brightness. Don't do that, you chief. See if you can answer some of these, folks, while I fiddle with the old phone. Notifications off, thank you. Don't need that. Telling me, oh dear. Yeah, so series circuit rules, voltage shared. That is rubbish. Let's write that properly. So we've got our series circuit rules. For series circuits, voltage is shared between components. Now, what do I mean the voltage is shared between components? I mean the power supply or the battery voltage. I'm just going to call it battery voltage is shared evenly, well, not necessarily evenly, that's a lie. It's shared between the components anyway. So there we go. And what we can say about the current is current same everywhere. So in a series circuit, the current is going to be the same everywhere. Okay, that's in series. So this question says the light intensity decreases. What happens to the potential difference across the LDR and the current in the LDR? If you can remember the graph I just showed you with the little burglar, resistance and light in a LDR, in an LDR by the way has that symbol with the circle, with the arrows, etc. So if you can remember that, that goes down. So it's saying as the light decreases, so as the light goes back this way, what happens to the resistance? Well, the resistance is going up, right, as it gets darker. So I can say resistance goes up. They haven't asked me about the resistance. But do you remember the relationship between resistance and current? If resistance goes up, current goes down. So in the dark, the current goes down with an LDR. What about the potential difference? Here's the difficult bit. If the resistance is increasing here, then its share of the voltage is also increasing. So if you don't know that rule, get to know that rule, because that might help you out tomorrow on a level 9 question like this. That's a level 9 one. So the potential difference is going to go up. If your resistance goes up, your share of the voltage increases. So you need to know that relationship. Okay. Now, let's go down here. What is the resistance of the LDR when potential difference across it is 4 volts? So what is the resistance in this LDR when the P Diddy is 4 volts? Check this. We need to go to our rules. If you know your series circuit rules, voltage is shared. So let's check it out. What is the resistance of the LDR? If that is 4 volts, what must the voltage be over here? If that is 4 volts, 12 minus 4, because the voltage is shared, is 8 volts. So this is 8 volts. 8 volts in a relationship, voltage and resistance are in a relationship, a mathematical relationship. So if this is 4 volts, what is its resistance going to be? Its resistance is going to be smaller. In fact, it's going to be half. So it's going to be 1,000 ohms. So that is going to be 1,000 ohms. And you can say its share of the voltage is smaller. it has half the voltage of the 2000 ohm resistor. So yes, this is triple, this is combined, this is both. So just learn that voltage and resistors in the sensing circuits are proportional. Okay, so they're in proportion. Now another way to work this out, I'll tell you the other way to work this out if you really want to know the other way to work it out. So we could have worked this out. There's another longer way to work this out. If you want me to show you the longer way to work this out, mathematical way to work that out rather than just doing ratios, we could have worked out that that is 4 volts, so that is 8 volts. We know the resistance is 8V and 2000, so I could do this. I could say V equals I times R, so which means I know that I is equal to V over R equals I. So I could go 8 over 2000 and I could work out the current going through this resistor. In a series circuit, the current is the same everywhere, so we could do 8 divided by 2000. This is the long using the calculations method. I'll work out that I've got 0.004 amps, and then what I can do is say, look, I've got the same amount of current going through there. I know the voltage is 4, and I can go 4. I can do V over I equals R, so I can end up doing 4V over 0.004 amps, and that is going to get you 1000. So you can do the other way to do it. There's more than one way to work out the answer. Anywho, let's move on. Calculate the current through the LDR when the resistance of the LDR is 5000. Give your answer to 2 sig fig. So for this one, I probably need to clear this, but I can't be bothered. So let's just work off of it. Right. If the let's clear that out. We got to clear it. We gotta clear it. We gotta clear it. Clear it. Clear it. Okay, I will be going through radiation. So, what do we call it? What we got here? Calculate the current through the LDR when the resistance of the LDR is 5000. So, if this is 5000 ohms, and they're saying calculate the current through the LDR when the resistance of the LDR is 5000, well, we can just work out the total. We should be able to just work out the total current here. So we know that, well, really easy. We know the voltage is 12. So it depends how we want to do it. That and that. Oh, easy peasy pudding and pie. Total, that is a fixed. I don't know why I'm waffling. This is a fixed resistor. So what this tells you is this has to be 2000. That can't go up or down. So what's my total resistance? My total resistance is 7000 ohms. In a series circuit, the resistance adds up. So I'm going to have V equals I times R. So I'm going to have 12V equals 7000 ohms times I, which is the current. So voltage is resistance times current. We can obviously see what we got to do there. We're going to do 12 over 7000, and that is going to give me 12 divided by 7000 equals bish bash bosh 0. Oh my days, 0.0017 ampos. I have to say, yep, you said, how do we know it's 4 volts and 8 volts? It tells us that one is 4 volts. There it tells us, what did it tell us? It told us the voltage was 4 volts, and then what is the resistance of the LDR when the potential difference across it is 4? Yeah, we know the total voltage is 12, and in series circuits, the battery voltage, which is 12, has to add up to the individual. So if they give you one component, you can work the other one out, right? 12 minus 4 is 8. So we know that's 8 because this is 12 for both of them. And if that is told in the question is 4, that has to be 8. And then you can go from there. Right. Got a little question for you here. This is going to test you. But before I do that, actually, let me just finish going through some of the rules. And then let me go through the rules on the old power and series level circuits. So I'm just going to go through the rules on the parallel and series circuits. So let me just smash. Oh, Sugar Ray Leonard. Let me just smash through the rules of parallel and series circuits. So have a look here. This is a series circuit here. It looks like parallel because of these voltmeters. Remember, voltmeters go in parallel around the component you're measuring the potential difference across. Ammeters go in series. In a series circuit, they're always going to be the same. So if this, in a series circuit, if this says 5 amps, then there's 5 amps everywhere, right? In the series circuit, it's the same. However, if this is an 8-volt battery, then if that's an 8-volt battery, then that could be, come on, mate. If the lamps are identical, it will be 4 volts and 4 volts, but they might have different resistance, different thickness of wires inside them, in which case that will be, Sugar Ray Leonard, that will be 5 volts and that will be 3. Notice the voltage in a series circuit is not necessarily the same. The current will always be the same, but the voltage isn't. We can then see that when you have a bigger voltage, your resistance is going to be potentially slightly bigger. So, yes. So we got V over I equals R. And you can see, therefore, the resistance here is going to be 3 over 5, so it's going to be lower. And the resistance here is 5 over 5, so it's going to be bigger. So when you have the bigger voltage in a series circuit, you normally end up with a bigger resistance. But you also have to know that the total resistance can be added up like that. So if I know the resistance of this, which is 3 over 5, so total resistance of this light bulb is 0.6 ohms. And if I know this one is 1 ohm, then it's telling you that 1 plus 0.6 total resistance is 1.6. So that is dead easy. Series circuits aren't so bad. Let's look at the parallel circuits. Parallel circuit, they are telling you that V1 equals V2. So voltage is the same everywhere. If this is an 8-volt battery, then this is 8 volts. This is 8 volts. I can add 100 of these. It will always be 8 volts, right? Now, the current divides along the branches. So this time, I get 5 amps coming down here. It splits into 2.5 amps here, 2.5 amps here, and it comes back. If I had an ammeter there, it will come back to 5 amps there. So in a parallel circuit, the current divides. Now check the unusual rule of resistance. There is an unusual rule to do with resistance in parallel. Notice these rules are swapped. So in series, voltage all adds up to that of the battery. In parallel, voltage is the same as the battery. In current, the current's the same. In series, the current's the same everywhere. In parallel, the current divides, so then adds up to the total current. Now, the difference with the resistance is, in parallel, total resistance is, this is the weird rule, is less than it's less than the resistance of the smallest, oh my god, resistance, oh my days, component. So this is a bit weird, but let me just mathematically show it for you. If we call this first light bulb here, this is light bulb 1, this is light bulb 2. If I want to calculate the resistance through light bulb 1, I'm going to do V over I equals R. So I'm going to do 8 volts over 2.5. What am I going to get if I do 8 over 2.5? 8 divided by 2.5. It's going to be the same for each one, but essentially the resistance is 3.2 ohms. Right? The resistance going through there is 3.2 ohms. Look what the total resistance is. Take the total voltage and the total current. So it's 3.2 ohms going through each light bulb, but look at the total resistance. The total resistance is 8 volts over 5 amps, because total voltage over total current, and we get 8 divided by 5. So this is a little trick with parallel circuits. Total resistance is always less than the resistance of the individual components. Bearing that in mind, let's have a go at a question that applies that law. Here we go. This applies this law. See if you can do this one, peeps. So have a look at this one, right? This little question only here. This says the student calculated the total resistance of 2 resistors. The student's answer was 26, so they added these up to 26. Y cannot be correct. They're saying the total resistance was 26. What did we just learn? This is parallel. These two are in parallel. What did we just learn? We just learned that that can't be the total resistance, right? Impossibilis. It can't be the total resistance. Total resistance must be less than 20 because it's less than the smallest resistor. So with the knowledge we have here, it must be less than 20. It must be like 19 ohms. Now, if I make this 7 ohms, look what happens. If that is 7 ohms and 20 ohms, look what happens. Let's say this is 10 volts. Oh my good gosh. Look at the resistance for each of these. Look at the 10 volts and I need to give myself 5 amps, right? So, well, that's kind of a bit crap, but yeah. The total voltage, the total resistance here would be 10 over 5. 10V over 5 would be 2 ohms. So look, total resistance is always going to be lower than these bad boys here. The total resistance is going to be lower than these guys. Anyway, enough of that business. We don't want to get on with that. Right, I'm kind of running out of time. I've wasted a lot of time. Wasted a lot. Oh no, hold on. We didn't do that equation over here. Let's do this equation. When the total resistance of the resistors is 7.5, let me rub out that nonsense I was writing over here. Listen, when the total resistance of the resistors was 7.5 ohms, the current in the circuit was 480 milliamps. Calculate the potential difference across the two resistors. So when the total resistance of the resistors was 7.5 ohms, the current in the circuit was 480. What is the total potential? Yeah. I'll go through some. You can call out some topics in a second. I'll go through them. All right. Well, the last half an hour, I'll just go through topics. So what you're going to do here is you're just going to rearrange V equals I times R. They've asked you to calculate V. So calculate the potential difference across the two resistors. Well, we know the total current, oh my gosh, I can't even speak, 7.5 milliamps. You've got to divide that by 1,000, so that's 0.480 amps. It's literally easy as that. And you're going to get 3.6. My days, isn't that nice and easy? There we go. That's the total voltage in the circuit. Oh, Why is it dangerous for the live wire of an electric cable to touch the case? So live wire is the brown wire. It carries 230 volts and the case will become live. If you touch the case, you will get an electric shock and be killed. There is an earth wire that should be connected to the case, in which case you won't be killed because the current will flow through the earth wire in case the case becomes live, and that will prevent that. Okay, so what do we want to do? All right, call out some topics and I'll do some speed revision before I finish. I'm not actually revising a lot tonight. I will be revising more for some of the others because I'll have more time. So some of the other exams I'll be revising a lot more. So if you tell me a topic, I'll revise it. What topic? Now, I haven't done static electricity. Let me smash through static electricity quickly then. Static electricity will take 2 secondos. So static electricity is involved when you have friction between, say, any two insulating materials. Insulators are plastic, so like this rod and this cloth. They have plus and negative charges like this, even amount, right? When you rub them together, you get friction of insulators. It's very important that you recognize it's friction of insulators. What will happen is negative charge can move, positive charge cannot move. So for example, in certain situations, the negative charge will move onto here, and now look, 4 negatives, 2 positives. This is now negatively charged, that is positive. So overall, this is plus, this is minus. We now have attraction, and that is static electricity. We may get a spark as if we put that near something metal, this may spark and we may actually get a shock as it tries to get to the earth. So that's static electricity, how it happens. Static electricity occurs when you have friction between insulators and negative charges move. And that is the most important thing to know. Couple of other things about static electricity before we go on. So you must have an insulator and you must have friction, and then negative charges move. Now, like negative charges repel and positive and negative attract. So really easy, right? If you've got 2 negative objects, they're going to repel. They're going to go away from each other. If you have 2 positive objects, they're going to repel as well, push away from each other. But just like magnets, if you have a positive and a negative object, they are going to attract to each other. Okay? You're going to get attraction. They're going to go towards each other. Now, when we draw the electric field around an object, let's say that, I don't know, your jumper becomes statically charged. We can represent your jumper. Let's say your jumper becomes positively charged. The electrons rub off your jumper. We can represent that as a circle with a plus in. And we have to show arrows at right angles going out. These represent the electric field around that jumper. So with the positive, if you're asked to draw a diagram to represent the field around a positively charged object, that is what you draw. Now, let's imagine a situation where the jumper is negative because negative charges have run onto your plastic jumper and got trapped there because it's an insulator. That will be because of friction. You've rubbed up against something, no diddy, and your jumper has got negatively charged. This is what it will look like. The arrows will now be going in. So when you draw a diagram of a negatively charged object, and this is for triple people, by the way, you're going to draw it like that. Okay? So just draw it like that, everything at kind of right angles to each other. You get the idea, right? You can just stick with 4 if you want. You don't have to draw all of those. Now, what is the definition of an electric field? So it is the field. If you're asked the definition of an electric field in triple, it's the field around a charged object where another charged object will experience a force. Okay, so that field, like the field around a magnet, but it's an electric field, if you put a charged object in there, it will experience a force. That force can be attractive or repulsive, depending on whether they're both negative One's negative, one's positive, or they're both positive. So the force could be attractive or repulsive, but any charged object, if it enters an electric field, it will experience a force. That's the definition of that. Right, let's smash off of that. Bush, bush, boosh. Because we're running out of time. Now there is a no. Here's an example of, for those of you that are into statics, here's an example. This boy has been walking on a carpet. The student becomes negatively charged, so he gets minus charges. How did that happen? Well, friction, it tells us friction, so we can't really say the word friction, but we're going to say electrons, or negative charge, rub onto socks. Where from? From carpet. So you can just say negative charge due to friction rubbed onto his socks. His socks are an insulator. I should mention that his socks are an insulating material, so they can't move out. Once they're on there, they're stuck. The negatively charged student touches a metal tap and receives an electric shock. So why would the negatively charged student receive, that's supposed to be negative charges, why would he receive a shock when he touches a metal tap? Well, when he touches the tap, he creates a circuit with the ground, and the metal is a conductor. So we want to say metal is a conductor. He creates a circuit with the ground. The electrons flow from the student to the ground. It's down a potential difference. So there's a higher potential difference in him than the earth. So you get a current flowing to the ground. So we actually get a current form because there's a potential difference between him and the tap. Okay, but we want to mention the tap is a conductor and he is being earthed. So that's why you get a spark. Now over here, this is just saying what I already did. So this is saying just what I drew just now. So you just bash them on like that. Right, you just bash them on, lovely jubbly. Some carpets have thin copper wires. The student is less likely to receive an electric shock when walking on this carpet. Copper wires are metal. They are conductors. They conduct the negative charge away to the ground. It earths the carpet. Therefore, he's still going to get friction, but the electric charge is going to move through the copper wire instead of into the boy. Anywho, let's get off of this. You can say charge is earthed. Now, what we want to do is, someone's been mentioning, what else? So I've done the electric field patterns, peeps. I just did those electric field patterns. Half-life. Someone mentioned half-life. I'm only going to say it because I can't be bothered to write it out. I ain't got that kind of time. I'm whizzing through what people are asking. So half-life is the time taken for half the radioactive isotopes in a sample to decay. You can also say it as the time taken for you can also say it as the time taken for the activity, which is a measurement of radiation. You can say it's the time taken for the activity of a radioactive sample to half. Or you can say it's the time taken for the count rate, which is a different measure of radiation, for the count rate of a sample of isotopes to half. So you can kind of say either one. Now, you will either have count rate or activity written here. They are two slightly different things, measured in becquerels. So you have your count rate. Now, the count rate, and you've got time. So they're two slightly different things. Count rate is how many particles enter a GM tube, a Geiger-Müller tube, per second. But that isn't the true amount of particles that are coming out every second. That is the activity. So if you were trying to measure me, and this is a Geiger tube, you're only going to get the particles going into the tube. That is the count rate. It's not the true amount because I got them coming off that way. I got them coming off that way. I got them coming off that way. So that's the activity. How many particles per second are decaying is the activity. How many particles per second enter the Geiger-Müller tube is the count rate. They're both indicators of decay and they're both Coolio. Right. Count rate. What do we do? If you're asked to find the half-life of substance X and that says 80,000, all you got to do is go to 40,000, go to 40,000, You're going to have a line on the graph like that. Draw the line across, draw it down, and wherever it goes there, so you half it, draw the line to where it meets there, and then you will get your half-life will be right there. Now you could do it again. You could half again to 20,000, draw your line across, and this time is going to be the same change in time, right? So easy peasy. You just half, you start from there and you half. Make sure you read the question carefully, RTFQ, and see what they say the starting activity is of the sample. Notice also that our half-life graph never reaches 0, because if you put a number in your calculator and keep dividing by 2, you will never get to 0. You can wait till the universe ends, but the activity or the count rate will never reach 0. It will still be halving until the end of the universe, okay? Because you can't divide something by 2 and get to 0. So the graph mustn't go to 0. Now, oh my gosh, we don't want to look at a coffee machine. You can say Geiger-Müller counter, Geiger counter, Geiger-Müller tube. Either is good. Doesn't matter. You will get the marks for either. Alpha, beta and gamma. Sorry, I ain't keeping up with the chat. Someone said alpha, beta and gamma. So very, very fast. I will just whip through alpha, beta and gamma because we're running out of time. So alpha particles, you can write them like that, but in AQA, depending on your exam board, they're the same as a helium nucleus. We can write them like that. Now they do have a 2+ charge. Why is that? They're made of 2 protons and they're made of 2p and 2 neutrons. There's no electrons, hence why they're positive. 2 protons and neutrons. So they're quite heavy. So you need to know they're heavy, slow, low penetration. They can't get through anything. They get blocked by paper, right? They're blocked by skin, blocked by paper. So what are the risks to you? Unless you swallow them, then you're screwed. But they're low penetration, low range. They can only go max about 5 centimeters in air. So low range. They're slow. They're heavy. However, they are highly ionizing. What does that mean? That means that if they bang into a DNA molecule or an atom, they can knock an electron off and cause a reaction. And this reaction, if it was in a DNA molecule, very unlikely, but if it got into your cell and got into your nucleus and hit your DNA, it could cause a mutation that could lead to cancer. And that is with anything that's ionizing. So alpha's the most ionizing, but the lowest penetration, stopped by paper. And you will get equations for alpha. I'm going to just do this in 2 minutes. You will get equations for alpha, and they are going to look like this. So you'll have like uranium 238 and 92, and then they'll say what type of decay is this, or work out what the missing numbers are. So let's just make out this is called X. So what would the 2 other numbers be? When you get a radiation equation, turn the equal, make sure the arrow in your mind, the arrow becomes an equal sign. So what would these 2 numbers be? Yes, yes, yes. Boom. 234 and 90. So that one's not too hard. Alpha is uber easy to spot when an alpha particle is decayed. Remember, they could add a beta on or a gamma on in the same equation. You might say, oh, I haven't seen them do that, sir. I have, obviously. But so across all exam boards and over time. So they may do that, and then kids go, oh my God, I've never seen it. Yes, they can do that. So, right, let's look at beta. Now, beta particles have 2 symbols, but you can go with that 0, -1, or most exam boards, E and a -1. Why do they use an E? Because a beta is an electron. And what do we know about beta? So it's more penetration than alpha. So it can go further, and greater range. I'm not going to write greater range because it's just too much writing. It can go like 1 meter or 2 meters or 3 meters. So beta can go a few meters, and it has more penetration. It's stopped by metal foil. So like aluminium foil or tin foil. That's what it gets stopped by. And it's less ionizing. Why is it less ionizing? An electron is lighter than 2 protons and 2 neutrons, has a mass of 0, so almost negligible, but it still does have mass, but it's almost 0. So it's less ionizing, It's still dangerous, but less ionizing, okay? Right, I think that's everything there. The other thing you have to know, which is a bit freaky, but I'm going to show you it in this one. So here we go. That is a carbon-14 isotope. Unstable nucleus. By the way, elements only decay if their nucleus is unstable. Check out the nucleus here. It's got 6 protons plus 8 neutrons. So 14 mass number altogether, and it's got 6 protons on the proton number or atomic number. Now, what's going to happen if it gives out beta decay? A lot of people flop shot this. They're going to write 7 here. I'm going to put nitrogen there. We don't need, like, they're going to write, 5 here. A lot of people are going to go 6 minus 1 equals 5. That's wrong. Think of that as an equal sign. So what must the numbers be from a nitrogen? What are the numbers from a nitrogen? Nice. We're going to have to do 7 because 7 minus 1 equals 6. And 14 plus 0 is 14. So those are your 2 new numbers, 14 and 7. Now look at what must have happened. Here's a key. You could be asked this for 1 or 2 marks. Here's a little key thing to look at. The protons here is 7 and the neutrons here is 7. So check out what they were before. What has happened? So we would say in order to form a beta particle, let's check this out. Carbon C has gained a proton and lost a neutron. How did that happen? How did it happen? Well, this is the exact definition for those of you that are on the that want to smash out a difficult question. So what we want to say is a neutron split into a proton and an electron. The beta particle is the electron that was fired out of the nucleus, and the neutron turned into a proton. So the proton went up by 1, the neutron went down by 1, and an electron was spat out. Essentially, it's telling you that a neutron is made of a proton with an electron stuck on it. That's beta. I can indeed. Sparky J10. Sparky J10. Boom. All right. Some people are talking about nuclear fusion and oh my gosh, I'm running out of time. Nuclear fusion and nuclear fission. Right. I didn't do gamma. I took too long. I'm running out of time, peeps. I'm running out of time. I can't get to everybody. I will be hopefully doing like longer ones for the other ones. 3-core cable, best trader, is just you've got a brown wire that's a live wire. Just think of it like this. If you touch the live wire, you're going to poo your pants, right? I would say SH something T, but that'd be rude. So you're going to poo yourself if you touch the brown wire. That's the live wire, right? And why? Because it's live. You'll get an electric shock. Because the live wire carries 230 volts and you're basically 0 volts. Think of diffusion. Potential differences like diffusion. So when there's a big voltage difference, you get a current. So between 230 volts and almost 0 volts, you're going to get a big fat current going through you to the floor and make you poo your pants. That's why we've got a brown wire on the live. Now the neutral wire is calm like the sea. It's blue. It's neutral. It has 0 volts. And the earth wire, think of forests and deserts, green and yellow, like the earth from an aerial view. That is the earth wire. That is also at 0 volts. But the earth wire is connected to any metal appliance, any metal case. It prevents them going live should the live wire accidentally touch the case. It prevents you getting an electric shock and saves your life. The earth wire has lower resistance than you, lower voltage than you, and so any current that is on the metal case will flow through the earth wire to the earth instead of through you. The neutral wire just completes the circuit and has to be at 0 volts. It completes the circuit. Right, anyway, that is the 3-core cableless, and of course they're covered in plastic because they're insulators. Right, what? Gamma, by the way, gamma's just got that weird funky symbol. It's like 0 and 0, 0 mass, 0 that, no mass, so it does not change any elements on its nuclear equation. They're going to stay the same. Right, gamma has the highest penetration, only stopped by thick lead, but it's the least ionizing, but it can go for miles and only stopped by thick lead. Right, somebody said... Songwaki alpha scattering did come up in chemistry as in physics as well. Alpha scattering is kind of simple. Really, it's the plum pudding model stuff you did for chemistry. So it's literally they fired alpha particles at the plum pudding, right? They expected this, so this will take, I'm only going to spend 30 seconds on this. They expected because gold atoms are big and alpha particles are small, all of the alpha particles to go through. What did they actually find? Remember, they hadn't discovered the nucleus. They didn't know about protons. They knew about positive charge and electrons. They believed that the alpha particles would just go straight through. What they actually found is pretty, most of the experiments showed that. So alpha particles mainly went straight through. This taught them that atoms are mostly empty space. So alpha particles went straight through. It taught them that atoms are mostly empty space made up of shells. I know they found that later. However, some alpha particles curved. And they went, hang on a minute, remember these are positive charge? This told them there was something positive in the middle, and because we got big fat deflections, it was very dense. So the outcomes, the expectations, expected observations were that alpha particles to all go through. They found that's true, so they concluded that atoms are mostly empty space. Conclusion 1. The second thing is that 1 in 10,000 alpha particles curved or deflected, or a very small amount curved and deflected. This told them there was a small, tiny, dense, positive nucleus. Okay, and that's what they learned from the ones that deflected or had huge deflections. Positive, small, dense nucleus. It did not tell them there were protons. It told them there was a small positive nucleus. They didn't discover the proton yet. So this discovered the nucleus. Right, anyway, let's move on. Someone said about nuclear fission and fusion. I'm just going to smash through nuclear fission and fusion very, very quick a lie. So let me smash through nuclear fission and fusione. So nuclear fission and fusion. Right, fission is like this. You have a neutron slaps into a nucleus, right? So let's just call this a nucleus. They might draw protons and neutrons. I'm not doing that. Right, so this is the nucleus of an isotope, a heavy nucleus, right? And it splits into light daughter nuclei. It splits into 2 daughter, or look, everyone's getting a bit excited nowadays, so I'm going to call it new lighter nuclei, right? Obviously it's going to be lighter because you've split it in half. So what else does it release? This is nuclear fission, by the way. It releases more neutrons. Ta-da! And energy. So if you're asked about nuclear fission, 3 products are new nuclei or daughter nuclei, neutrons and energy. 3 things are made from nuclear fission: new nuclei, neutrons, energy. Now you can get a tricky equation with this where they say this is 2, 3, right, where they go like 2, 3, 6. I'm making these numbers up because we're being swift. So 2, 3, 6 and 100, right? If I split this and say that is 136 and 50, people are going to assume, oh, if that's 136 and 50, then that must be 150. Now that would be lovely, but we forget that neutrons each have a mass of 1, and we must include this. So actually, if I was to write this as an equation, add that neutron to that on the side of the arrow, and you would have 237 and 100 on this side of the arrow. And then I've said there's 136 and 50 over here, right? And then I'm saying, oh, what are these 2 missing numbers? But we mustn't forget the 3 neutrons. So essentially, I'm saying, oh, 136, that's not 30, by the way. That's supposed to be like 3 neutrons. So I could have just rubbed that out. I'm making it more confusing, but just take into account that I'm just trying to point out you might get that trap. You might miss out that neutron there. Add that to make that 237, and that's still 100. So then when you do that, you're going to go 237 minus 136 minus 3, so minus 139, and you'll get whatever you're going to get there. I can't even work that out myself. And then you're going to do 100 minus 50. So yeah, that would still be 50. That would definitely be 50, but this one is going to be slightly different. So whatever you guys, if you know what that would be, you would do 237 minus 139. So just remember that, because then neutrons come off. That's nuclear fission. Nuclear fission is done in a power station, and we use something called control rods to control the rate of nuclear fission. How do they do that? Control rods, which are made of boron, absorb some of the neutrons. Why is it a chain reaction? You also need to know that it's a chain reaction. Each one of those 3 neutrons, sometimes it's 2 neutrons depending on the reaction, sometimes it's 3 neutrons or 4 neutrons, but each one of those neutrons will go on and crack another atom. So you'll start with one nuclear fission cycle, and then in the second stage, if it was 3 neutrons, you're going to break 3 atoms, and then in the next stage 9 atoms, in the next stage 27, and then 71. You get the idea. It's tripling each time. That's why we call it a chain reaction. Okay, so if you want to control the chain reaction, you need to use control rods to absorb that. Now nuclear fusion is slightly different, right? You get like 2 hydrogens and you lick them together, but what you need to know is that you have to have that's the key, high temp. This makes it dangerous and too expensive, so we don't do nuclear fusion and high pressure. The benefit to nuclear fusion is there's no radioactive waste. Nuclear power does not produce greenhouse gas. Enough people think it produces carbon dioxide. It is non-renewable, but it doesn't produce any greenhouse gases. So just remember that if you're asked about nuclear power, that is not a disadvantage that it makes greenhouse gases. It doesn't. What nuclear power does produce is toxic waste at the end of it. The control rods and the fuel rods are toxic. Anywho, if I slap these two together, because this is fusion, you're fusing, you would think I'm going to make a new thing like helium, like that. What you do have to know in AQA, and crap loads of energy. So it's like loads of energy. So I know that I said there's energy in nuclear fission. If you think the energy in a nuclear bomb is big, nuclear fusion is a million trillion times more energy, right? So nuclear fusion is what's powering the sun. So every time you walk around, every single plant, every tree, every human, every animal, everything that's alive on the earth is powered by nuclear fusion from the sun every day. So it makes millions times more than nuclear fission. Now, what you do have to know, you don't have to explain it, but some mass is lost. E equals mc squared. Einstein said that. Some of the energy that is produced comes from the fact that there is some mass loss. You don't need to explain the mass loss, just that during fusion you get mass loss. Anyway, bosh, that's that done. Right, someone said something about a question. He was back here somewhere. Someone said something about a question 19.1, 18.1, 19.99, 9791, 923, 456. So can you go over question 8.4? This was Sparky Junior 10. 8.4, 2019, specific, latent and specific. What? Let me see if I can do that one for you right now, dude. And we will go through the question with 5 minutes. With not long to go, because what did you say? It was 2019. Am I on combined, or am I what the ass? Did you say 8.4? Oh yeah, we do. Oh, fudge. Bear with me, folks. Bosh! So this is Sparky Junior's one now. Whatchamacallit? Okay, I am running out of time. This is probably going to be it, folks. Okay, this was a dirty one, but this was like what they do in higher physics. They get you to apply, and there's actually 2 equations here: specific latent heat. Oh my good gosh, have I got that specific? Where's the specific latent heat? Where is that? Because I just like mashed that off there. There is specific heat capacities there. Where are you, latent heat? Latent heat is just oh, there it is. E equals ml, right over there. Right, so how are you going to use that? You're going to go, right, they have mentioned the specific latent heat and specific heat capacity, so hopefully your first step towards greatness is to circle these two. Bish, bash, bosh. And then you're going to write those down. So I know my face is over that. I ain't got that kind of time to be fiddling about. So we're going to go... Oh my gosh, Tom, sort it out, mate. You're running out. You're running out. The clock is ticking. MC delta theta. And then we're going to go... No, don't do that, you Wally. We're going to go energy equals M times L. Right, we've got two equations. What do they mean? Well, I'm going to get rid of this. And I'm going to get rid of this. Because I need a little bit more for explanation. And then I'm chipping off. Now, as I said, in other exams like P2 and that, I will have more time. This one, I've got a clash today, so I ain't got the kind of time that I would have liked to dedicate to the Physics GCSE. So, calm now, star. Right, let's read this question. Ice cube has a temperature of -15. Total thermal energy needed to raise the temperature of the ice cube. Check what I'm doing here, peeps. We got a little graph. It's called a heating and cooling graph. So we're going to go Bosch time. And we're going to write temp here. Okay. Ice. Ice baby. Bum 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 bum. And then we're going to go, oh, sugar. Come on, Tom. Sort it out, you chieftain. Anyway, we've got like a heating and cooling curve. Oh, I won't bother doing all of that. Right, it's getting too much. So a temperature of -15. So they're saying this is -15. It has to be raised to 0. So that is this part of the graph. When you're heating on a heating graph, this part of the graph is going to be, we're going to find the energy used to heat the ice by doing delta E is equal to the mass times C times temperature change. Now, the total thermal energy needed to raise the temperature of this ice cube to 0 and then to completely melt the ice is 5848. Now, what is happening on the straight bit of the graph? That is the change in state. So this would be melting would happen here, and then boiling would happen here. Now this is known as the specific latent heat of vaporization, and over here this is the specific latent heat of fusion. So this is equal to E equals M times L. So what they're essentially telling us is the total amount of energy, the 5,848 joules, 5,848 joules was the total energy to heat the ice up to there and then to melt the ice. Remember, the temperature doesn't change, but you still gain energy. The Bunsen burner is still on, but the temperature's not going up. And the reason is, on the straight part of the graph, the internal energy is increasing in both parts of the graph. So internal energy is increasing here and increasing here. The internal energy is increasing here because the particles are gaining kinetic energy. Right? They're moving faster. They're gaining kinetic energy. The internal energy is also increasing in the straight part of the graph, but not because the temperature is going up. Temperature is proportional to kinetic energy. The particles are not moving any faster when they're melting. They stay the same speed. In fact, what's happening is their potential energy is increasing and they're getting further apart. They may ask you about this on a 6-mark solid, liquid and gas question. So when we turn into a liquid, at the point we melt, we do not gain any speed, we do not gain any kinetic energy, but we still increase in internal energy because the particles get further apart, they gain potential energy. And internal energy is equal to kinetic plus potential. Now, what is all this about? Well, they're essentially telling us that 5,848 joules is equal to the energy, that's energy. So E, the total energy, total E is equal to M times L equals M times L plus M times C times change in temperature. So it's the specific heat capacity plus the specific latent heat of fusion in this case is equal to the total energy. And they're saying work out the mass. So all we've got to do, peeps, is work out these numbers. So they've told me the specific latent... Right, that's M times 334,000. So I've got 334,000 M, right? Plus, oh my good gosh, what is that? That is 2,100 times the change in temperature was 15. So let's do 2,000. Oh my gosh. Come on, switch on, calculator. It's gone cold on me. 31,000. Right, so 31,500 M. Now, 5848 is equal to 334,000 plus 31,500. Let's whack them together. And if we whack them together, 31,500 plus 334,000, we're going to get bish bash bosh 584 is equal to 365,500 M, right? M's the unit, like kilograms. So it's really like saying 334,000 kilograms plus 31,500 kilograms. It's not the kilograms, by the way, yet, but it is like the kind of unit, right? And that's what it's going to work out as. So we don't add M together. Sugar Ray! Oh, there we go. We don't add the M's together to make like 2M. So now all I got to do is 5848 over 365,500, and that is going to equal M. And bish da bash da bosh d 5848 divided by 365,123 gives me 0.016 kg, and you get 6 Putman marks for that one. Now, yeah, 0.016. Yeah. So you just got to remember the straight bit, the flat bit, the flip bit, the flop bit. Listen, I got to shoot, guys. All I can say is good luck. Is it a morning exam tomorrow, by the way, for physics? Is it morning? Is it morning? Morning exam or afternoon? What is it? Morning or afternoon? Okay, fair enough. Fair enough. Okay. Cool. Okay. Oh my gosh, Lion's getting a bit excited, isn't he? Oh my god. We got a bit of a dweeb in the chat, peeps. We got a dweeb in the chat. Dweebosh in the chat. Oh my days. Right, what should we do? I think it is going to be time to go. So, yeah. We don't want to ban people for no reason, so. Cool. Nice one, guys. Sorry I couldn't go through more. Otherwise I let down the chemistry students. I got to bust some chemistry, so otherwise I'd go for more. Yeah, I don't want to hurt anyone. I don't want to put up any stupidness. I have stupidness for people, but everyone's been very nice today. Well, I don't really look at the chat, so you know what I mean. So there we go. What can I say? Well, you say that, but I should have been on for longer. But what are you going to do? So. Yep. I didn't even get to play my. No one was acting like a gangster in the chat. I didn't even get to play my little gangster thing in the chat. Yeah, like, you see, the problem with Lion is he thinks he's a gangster. Yeah, you know who that is, don't you, folks? In the chat, we know who that is. All right, guys. We don't want to say too much, but we all know who that was. All right, guys. I'll see you a lot later, and I'll be back for the other GCSE exams, where I should, if there's no clashes, be able to do a bit of a longer one and cover all the materials. See you later.
You're still here? It's over.